And what I'm going to do also is we're waiting for another school to join. And
What?
Raphael, I hope Richard comes back, and I hope Matt comes back to this call.
Hope so too.
I guess in a minute or so you might have to go hop over too, and hopefully you don't get stuck there.
It sounds like you were able to go back. You were able to connect to the Zoom call easily, right, Stefan and Raphael?
Yeah.
Okay. Worst case, absolute worst case scenario, if you have a second device to run a second Zoom call with, that way you can have both the Lake Zoom call running and this one, in case Matt is not able to come over.
Oh, yeah. Hop on a different call.
And Shanti Bhavan, in a moment, I'm going to describe what this telescope is that we're using, what kind of science we're doing, who we are, who are the people who are connecting with you on Zoom. But I'd love to get an introduction from all of you. Tell me which class you are, and are there teachers in the room in addition to the students?
Yes. Hi, I'm Brianna.
Hi, Brianna. How are you?
I'm good. How are you?
Good, thank you. Good. And thank you for hopping on this call right away, and sorry for the change.
Oh, no problem. We're all very excited.
Very good. This is classes 11 and 12, or 10 and 11?
10th and 11th, yes.
11, okay. Wonderful. And I understand there are 29 students in the room. Are you in the library room right now?
Yes, 28.
Oh, 28.
28.
Okay.
And 29 including you, Brianna. Are there any other teachers?
Yeah, 30. Yes.
Yeah, that's 13. Miss Agaya in the back.
Hi. And I think this is the library room that I was in with Anand a few weeks ago.
Oh, yes, you recognize it. Yes.
Yeah, I recognize all the books on the shelf. Wonderful. So classes 10 and 11. That means you must be like ages 15 and 16, or 16 and 17? 16, 17, right?
15 and 16 and 17.
15, 16, and 17.
15, 16,
we have
and
a variety of.
Excellent. And again, I'm waiting to do the introduction of our team. I'm still waiting for the other school from Kolkata to join. But I will, if they don't join, then we just go ahead with our introductions.
I don't know for sure. Oh, there's
Matt.
But I don't know for sure, but Monica also said she might be joining the STS session. So
okay, shall I send Monica the new link?
Yeah, I put it on Slack. So hopefully.
Although she did laugh when I told her what time it was, so I'm not sure she's actually joining. I don't know if we actually.
That's fair enough.
I don't know if we actually got a confirmation that she was joining, because when I said it was at midnight, she just started laughing. So I was like.
And so for the, let's see, I'm going to try one more time to see if the Kolkata group is going to connect. Just give me a moment. Okay, let's get started.
Thank you, Richard.
I think we should get started with introductions and go around the room, and then we'll go back to the screen share in a moment. That's okay. So the Shanti Bhavan group has introduced themselves there. If I can repeat, ages 15, 16, and 17. These are classes or grades 10 and 11. The grade 10, you must be getting ready for your board exam at the end of this academic year.
Yes.
Yes, I don't want to remind you of something unpleasant, but I know. And then, okay, so, and you're in the state of Tamil Nadu, if I remember correctly, in the northern part of Tamil Nadu, near Hosur, right?
Yes. Yes.
Okay. So let's go around the room and do introductions. Raphael, since I see you on my screen, then we'll go to Matt, then Stefan, Richard. Go ahead, Raphael, take it away.
Sure, yeah. Hi, my name is Raphael. I am currently a master's student at San Francisco State University. I did my undergrad at University of California, Santa Cruz with Raja as my mentor for research. I've been working on this project since 2019, I believe. So it's been a few years now. And I did my undergrad work on classifying the variable stars from this project that didn't have any prior classifications. I'm still kind of working on that in a general sense, but hoping to also look into some of the more particular like red and blue stars that we observe. Yeah, it's kind of a little general tidbit for me, I guess. We can move to, I think you said Matt next.
Hey, my name is Matt. I am the telescope technician here. Before here, I was in the military. I worked on helicopter electronics, and I also have a patent for a folding spoon and like to do a lot of like technical stuff. That's about it.
I think you're muted right now, Raja.
Matt, you're on a mountaintop in California right now where the telescope is.
That's correct. Yeah, we had some dew earlier that condensed all over anything cold, and I opened the telescope shutter about 30, 40 minutes ago. I thought it was going to be dry, but it's still wet. So I've spun the dome 180 degrees to see if the wind will dry it off. I'll probably open it again here pretty soon to check.
Muted again.
Sorry, I keep muting myself. So Shanti Bhavan students, two of the people who introduced themselves, Matt, it says 120 ROR. 120 inches is the diameter of the telescope. ROR stands for readout room. That's where the data come in. And Matt is physically located in a room that's literally adjacent to the telescope. The telescope room is kept cold so that it's at the same temperature as the atmosphere to minimize turbulence. And so Matt is in California, closest to the telescope. Raphael must be the second closest, I'm guessing, because he's in San Francisco, which is about a two-hour drive. Oh, hello. Future Hope is connected. Kamarjit, hello. Good afternoon. We're just doing some introductions. Raphael is also located not far from the telescope in a relative sense. He's probably 2 or 3 hour drive from where he is all the way up to the mountaintop. And let's go to Stefan next, and then Richard. And please, Stefan, when you introduce yourself, tell people where you are physically located.
Yes, hi, my name is Stefan Kimura. I'm usually the one who was running the telescope, but we've been letting Richard run it as he's been getting checked out this weekend. But I graduated from Willamette University with a degree in physics in 2018, and I'm debating if I want to go back and working to go back to get my master's or my PhD in astronomy or physics right now. I guess the second newest member, or no, I guess third newest member of the team now. I've been joined about a little over 2 years ago now.
And
And
Stefan,
I am from the Big Island of Hawaii. I'm doing this all remotely as well.
and are you in Kona right now, Captain Cook?
Yeah, I'm in Kona. Yeah, Captain Cook. So I guess that makes sense, or I guess that's important because Richard is also from the Big Island.
Richard is also on the Big Island. So for the students who've just joined from India, Future Hope has joined from Kolkata. They've joined from Kolkata, and then for the Shanti Bhavan, you guys are joined from Tamil Nadu. You can see already that there are many parts of the world that are connected on this Zoom call. So Raphael and Matt in California, Stefan is in Hawaii, Richard will introduce himself. Richard is in Hawaii as well. Different part of Hawaii, different part of the same island. So Richard, take it away, please.
We join a meeting to call.
Hi, so I've got my camera on. Yeah, I'm Richard Smith. Yeah, I'm in Hilo, which is on the eastern side of the big island of Hawaii. Well, I arrived here about a month ago now to work at the Gemini North telescope. And yesterday was my first day doing this telescope operation, so I'm very new to it, but I think I'm doing okay. Yeah, originally from England, and I went to Queen's University in Belfast. So I've been hopping around the world a bit. Yeah.
Richard, I'm looking forward to meeting you. Looking forward to meeting you in person when I go to Hilo in early October. Okay, so next we'll have Future Hope introduce themselves. Shamarjit and Minu, and I don't know if Shujata is there. If you want to turn on your video and introduce yourself, that would be great.
Hi, we were as usual having some technical problems, but just give us a minute.
No problem. No
we'll
problem.
just
We'll
get
come
it.
back to you. We'll come back to you. No problem. Ted, would you like to take a moment to introduce yourself? It's nice to see you, Ted. It's been a long time.
Hi, everyone. This is Ted. I'm from Shanghai.
Wow. So we have California, Hawaii, China, and India connected on one Zoom call. Very different time zones. What time is it for you, Ted, right now? 8 in the evening? Sorry, 7 in the evening. Right?
Yeah, well, it's 6 p.m. Well, yeah, it's around 6 p.m. right now, 6:40 p.m. roughly.
Got it. Got it. And Ted, I'm so sorry for being slow with my responses. So we should definitely go ahead with the MOU. I would love to catch up with you. We should set up a Zoom call to do this sooner
Sure.
rather than later. Oh, there we go. I can see the students from Future Hope. I recognize you because I saw you in person just 2 weeks ago. Future Hope, let's take a moment to introduce yourselves. Shamarjit, I can see you and I think we can hear you now. If you unmute yourself, your connection is muted right now.
Your name and your class. So let's start.
My name is Vikas. I studied class 10.
Yeah, I remember you. I remember you from our visit. So which class is in the room right now?
So they are mixed.
Mix. Okay, which classes?
10 and 11.
9, 10, and 11? 9, 10, 11, and 12. Excellent. And Shamarjit, would you like to introduce yourself, please?
Okay, hi, I'm Samarjit, the Director of Operations at Future Hope. We are a school and homes, and basically we look at children from vulnerable areas and difficult circumstances. And ours is possibly the only free school in India which has got a CBSE, which is a academic accreditation that's given to regular schools, but not to free schools. But possibly we are India's only school that's got this accreditation because of the kind of work that we do. We have classes still from KG to 12, and we've got labs, classrooms, and other stuff, activities. And today what you see are these students who are primarily interested or are doing science. So that's why they are here. And we also have a teacher here, Sushmita, and our librarian, Kaya.
Oh, hi. Hi, Shushmita. Hi, Kaya. Okay, I see we are using your Zoom link.
Hello, sir.
Hello. Hi. You're just off camera, I think. And I know you missed this earlier. Hi, Kaya. I know you missed this earlier, but what you see as SB on your screen is Shanti Bhavan, and they are a school that is located in rural Tamil Nadu. Oh, there's Stefan. I can see Stefan's video. Hi. And so Shanti Bhavan is located I guess, a 2-hour drive from Bangalore, but it's in northern Tamil Nadu, in rural Tamil Nadu. And I had the privilege of visiting their school twice. I've now visited Future Hope just once. I think with this, we should go into what science we're trying to do. If one of you want to share your screen, I suggest we look at the OBJ2 spectrum, the fast radio burst spectrum, host galaxy spectrum. We can talk about spectra and what we're doing on the telescope tonight. I'm happy to say a little bit about the telescope. I wrote a brief amount in the description of the event. The telescope we are using tonight is actually a historic telescope. It was established, the observatory was established in 1888. So well over 100 years ago. 1888 means 100 and, if I'm doing my mathematics correctly, 135 years ago is when the observatory was established. Turns out this observatory is the oldest continuously operated mountaintop observatory in the world. It was over 100 years ago that people realized that putting telescopes on mountaintops provided an advantage. Advantage in terms of being able to observe the skies with greater precision. When you go onto a mountaintop, what happens is there's little less of the Earth's atmosphere above the telescope than there is at sea level. If you put the telescope at sea level, there's a lot of atmosphere above the Earth's atmosphere. All of the Earth's atmosphere is above the telescope, and the Earth's atmosphere glows. The Earth's atmosphere is turbulent, so there's distortion of images, of astronomical images. So people realize that going up to mountaintops is an advantage. Now, of course, going up to mountaintops 150 years ago, 130 years ago was not easy because you had to go up by horse-drawn carriage. Roads were not very good. So there was a challenge, but also an advantage. And Lick Observatory was the first observatory to really start continuous mountaintop observations in 1888. The telescope we are using tonight is not that old. It was, I believe, Matt, you can correct me, I think it was in the late 60s or early 70s that this telescope was bought from Palomar Observatory and polished, ground and polished into a mirror, either late 60s or early 70s. And this is a 3-meter telescope we are using. That means the diameter of the telescope is 3 meters. And it's a single mirror. It's got a hole in the middle, and that's for a particular style of focal design called Cassegrain focus. And 3-meter telescope, we're using what's called a double spectrograph. I should let the others describe what we're seeing on the screen and what a double spectrograph is. What you're looking at right now is a spectrum of a galaxy. A galaxy that had something interesting happen in it, something called a fast radio burst. This is an interesting type of radio pulse that was sent out from this, that came out of this galaxy. We think we understand the physics of this, but it's still something that's at the cutting edge of our knowledge. Wow. So you've got emission lines for this galaxy. I'd like to see that.
Yeah, so this is the second one that we observed for that night, and we actually got some an emission line on the red side as well, which is exciting.
Show me the emission line if you could zoom into that.
Yeah.
Oh, there we go. I see it.
Yeah, and it showed up on all 3 exposures, so pretty confident on it.
And what I'm seeing is actually a double emission line. I can see a fainter emission line right below.
Right next to it. Mm-hmm.
Yeah, and the let's see, shorter wavelengths.
There's a skyline there too, but
yeah.
Sorry.
And sorry, shorter wavelengths are towards the top, right? So wavelength is increasing downwards, or is it the other way around?
Yes. I think the top is long wavelength. The red spectra, like this red CCD is weird, where smaller values are longer wavelengths, I think.
So I thought longer wavelengths are towards the bottom. Can we scroll? Can you just
I could be wrong.
pan down a little bit? I want to see what the rest of the spectrum looks
I
like.
actually wrote
I thought it
down-
was I thought it went what do you call it? From the bottom to the top, left or what do you call it?
Yeah, bottom to the
high.
top. Yeah, bottom to top, the wavelengths get longer.
Pretty sure, yeah, if I recall correctly.
Keep going down a
We
little
try to
bit
take a
more.
slice too if we need to.
Take a little column slice of the spectrum to see what the 1D spectrum looks like.
Yeah, and especially if you could zoom in around the emission line and take a slice. Yeah, so in fact, I know some of the wavelengths here. If you look at you see this two sort of fuzzy bands near the bottom. That's 8660. The dark line in the middle is about 8660. In the middle of that. In fact, if you take a cut there, you'll see that looks like a sort of accordion shape. It has the fuzziness is caused by many faint lines. So that's at 8660. And if we go up to the where the emission line was, should be able to see that. I think it's a doublet.
I think it's higher up.
Yeah, it's a little bit higher up.
So is that absorption? Yep.
Yeah,
there
that
it is.
absorption is at 7600. That's the A band. You see the strong absorption below that, a little bit lower, little lower,
Could actually
even lower.
calculate the wavelength right now.
You see the very strong absorption right below your cursor. That's the atmospheric A band. So when you see something dark, for the students who are watching, when you see something dark across the screen, it means something is absorbing the light. And in this case, the oxygen in the Earth's atmosphere absorbs the light. And that happens at a wavelength of 7600 angstroms or 760 nanometers. And so this particular emission line, it's showing up at a slightly shorter wavelength than 7600. Are you able to calculate the wavelength?
What pixel is it at? That's row 1809.
Row 1809, okay.
Okay, so it should be around 7650. I did lots of wavelength calibration stuff earlier
It
in the
should
night.
be less than 7600.
It might be.
Can we take a column cut there? And then can we zoom in on the, I want to see if it's a doublet. I think it's a doublet. So this galaxy is so far away from us that light from the universe has been stretched out by the expansion of the universe. Between light leaving that galaxy and reaching us, the universe has been expanding, space itself has been expanding, and this all wavelengths from this galaxy. The galaxy's light, by the way, is the vertical streak that you see going across, the vertical streak. Yeah, exactly, that you see. Stefan, that's you running the cursor up and down, right? So, no, Richard is running the cursor up and down. Sorry, Richard, that's you running. Okay, so if we were to zoom in to the pixel number that you said was the wavelength of the...
Yeah, about 1810.
Yeah. Where is 1810 in this? Is that 1810?
Yeah, that bright peak is 1810.
And wavelengths are increasing. So the brighter of the doublet peak is, if that's a doublet, I'm not certain. The brighter of the doublet peak is at bluer wavelengths.
Yes. Bigger pixels are
yeah,
smaller wavelengths.
Yeah. So I'm not convinced it's a doublet, but it's definitely an emission line. And whether we can use it to get typically you need more than one to get a redshift. but
Mhm.
can we scan and see if there are any other emission lines?
There might be one right next to it. Just looking at the spectrum, like there's a skyline right there too, but
Right below it, right?
it's not creating as much of an impact on the spectrum than
Yeah, I see what you mean. And, you know, one will have to do the data reduction of removing the night sky lines. And I
Mhm.
think then it will pop out.
Yeah, I think so too, because like, yeah, if we look at the other skylines next to it, then they
Yeah.
also impart onto the continuum a little bit, but that skyline seems like it imparts way more. So
Yeah.
it will extract some residual signal from that.
Yeah. And so for the students, the the horizontal lines that you see are produced by the Earth's atmosphere. The Earth's atmosphere glows at every wavelength. And so all the horizontal lines you see are produced by the Earth's atmosphere. And so what we do is if we're interested in a particular object in the sky, a particular light source in the sky, this particular light source is of interest because, like I said, there was a burst of radio emission from this galaxy that was detected recently by a telescope in China, by the CHIME telescope in China. CHIME is the name of the telescope. And some of our colleagues are involved in that study. And when they saw that there was this burst of radio emission from this point in the sky, they found that there's a galaxy there. And now we are trying to help them measure how far away this galaxy is, or what its redshift is, how fast it's moving away from us, or how much space has expanded between between when light left this galaxy and when we're observing it now. Yeah, I'm just looking at the red box that Richard is that says plot, where Richard's cursor is. That's spectrum. Now, we are normally used to looking at a spectrum of the sun. When you look at a rainbow, you're seeing a spectrum of the sun. But this is a more technical way of looking at how you take light from an object, okay, an astronomical object, and you spread it out into its constituent colors. Every color has what's called a wavelength associated with it, wavelength or frequency. So what is being plotted on the x-axis is something like wavelength, increasing from left to right. And what is being plotted on the y-axis of the graph that says plot is how much energy is being emitted by that astronomical object at each wavelength. And if you go to the far right, you'll see that accordion feature, far right. You see that double, right there. Oh, hi, Manan. Yeah, if you could zoom in on that, please, that would be great. Perfect. Yeah, that, those two broad peaks with a dip in between, that's at 8660 angstroms. And now if we zoom out, we can see the A band, which is at, the A band is the dip at 7600. Let's see, here's what I can do. Can I request, I wonder if I can request remote control from you.
Yeah, I think if you go to the view options and request remote control.
There we go. So if I, oh.
Sorry, 1 second.
Sorry.
Yeah, that should be working now.
Yep, it is. Thank you. This is the marvels of technology. I'm actually, this is happening. Actually, the computer that is hosting this plot is on a mountaintop in California. Richard is connected to that through virtual network computing, VNC, and then I am controlling Richard's screen by through Zoom. And after I've selected the box, what do I hit next?
Apply box, and that should zoom it in. Yeah.
Okay, so this dip over here is at 7600. So if we go back to the full screen, how do I do that? By going to
No zoom.
No zoom,
The
just a
button.
little lower.
there we go. Okay, so this is at 7600, and this is at 8660. So that's 1000 angstroms from there to there, whatever the pixel numbers are here. I can't quite read the pixel number here. Row number, rather. What's the Y coordinate?
1633, I think.
Okay, and how about if I'm here?
Oh, the Y coordinate, my bad.
Let's start with this.
That one has a Y coordinate of 1010, but an X coordinate of 914.
1010, okay. And then now?
That one's Y coordinate is 993 and X is 1633.
I think it may be, I think we need X, not Y, somehow.
I do think we need X too, yeah. When you take the column slice, it plots
Translates that, yeah.
yeah.
Okay, so what is the X coordinate here?
That one's, 809.
And here?
That one is 1633.
Okay, so here's what's going on. 809 and 1633, so the difference is 800 pixels, or 820 pixels, 825 pixels. Now, this strong night sky line that I'm circling, that one is this night sky, this set of night sky lines right here. So the emission line, and then you can see that there is a desert where there's no emission lines, and that's this desert up here in the spectrum. So we are seeing this set of emission lines and this set of night sky atmospheric and glow lines, and then the galaxy's emission line is somewhere there. So I would estimate it's somewhere where my cursor is, which has an X coordinate of
1763.
Okay, so that's another 100, 130, 1630, 1760, 100, another 130. It looks like the mapping is something like roughly an angstrom per pixel, right? Because
I think it's like 1.3.
1.3, okay. So this 130, so that means another 160 angstroms. So I would, if I'm doing the math correctly, about 7330 or 7340 is the wavelength of this emission line. And so for the students, what we're trying to do is translate from the pixel coordinates in our silicon detector to something that's more physically or astrophysically meaningful, which is the wavelength of light that's landing on that pixel. And this is normally done through a process called wavelength calibration. But why don't we take a quick pause here and see. I'm going to give priority to the two schools, so Shanti Bhavan and Future Hope. You're both muted right now, but if you have any questions, this is a great time to ask. And Manan, welcome. It's good to see you. Okay, who's going to ask a question?
Hello, sir. I am Bhatika. My question is here spectrum emission and absorption occurs through which emission occurs.
I had a difficult time understanding your question. Can someone repeat, someone who's closer to the microphone, repeat the question, please?
Okay, so sir, hello. The reason she's asking is why this is happening, the starter and the
Emission and absorption occurs sunlight
forward.
Due to sunlight, emission occurs or due to some other radiation?
Due to sunlight, this is occurring or any other radiation?
No, this is not being caused by sunlight. Yeah, this is important. This is right now in California, it's nighttime. So we're not seeing any sunlight, but we are seeing two there are two reasons. This is a very good question. There's two reasons why we are seeing light when we take a spectrum. By the way, this spectrum was not taken tonight because the telescope is still closed tonight because of the wetness of the atmosphere, of the rain. But this was taken last night, just 24 hours ago. And there's two sources of light here. The horizontal bands are coming from the glow of the atoms and ions in the upper atmosphere of the Earth. So the Earth's atmosphere, even when it seems like it's completely dark, the Earth's atmosphere actually glows slightly. So with a powerful telescope, you can see the glow, and that glow is producing these horizontal lines. Now, the second thing that is producing light is we pointed the telescope towards in the direction of a galaxy, and the galaxy's light is showing up as the vertical band in this vertical band in the thing that says untitled. The vertical band is coming from the galaxy's light. So the galaxy is made up of stars, and we are stars like the sun, and we are seeing the light of all those stars collectively, the light of all the stars that make up the galaxy. That's what's producing the vertical band. Did that answer your question?
Thank you.
Did that answer your question? Thank you. Thank you. Any questions from the Shanti Bhavan students? Shanti Bhavan, this is your first time taking part in Shadow the Scientists. The Future Hope students, last September, I think they took part in Shadow the Scientists 5 days in a row, 5 nights. We were using a different telescope in Hawaii, but I think the Future Hope students took part Monday, Tuesday, Wednesday, Thursday, and Friday of that week. It was almost a year ago in September. So Shanti Bhavan, if this is all new to you, it's because, of course, this is the first time you're taking part in Shadow the Scientists, but please feel free to ask a question, and no question is a bad question. We will certainly do our best to answer any question you have.
So, Mr. Raja.
Yes, please.
The light coming from the other universe. Have you guys found out the distance from where, or from the distance between us and that light coming, where it's coming from?
You said other universe, but you mean another galaxy?
Okay, the other galaxy.
Yes.
Galaxy. Okay.
Yeah. And your question is, how do we find the distance?
How do you find the distance, and do you guys know the distance of the light that's on the untitled?
No, that's a good question. The way we and who's asking the question? Sorry.
David.
David. Hi, David. Okay. So the way we get the distance is slightly indirect. We know that the universe is expanding, and this was measured by a very famous scientist named Edwin Hubble in the 1920s, I think 1926, 1930s. So we know the rate at which the universe is expanding. So if you measure how fast something is moving away from us, or something called its redshift, if you can measure its Doppler shift, then from that we can indirectly measure how far away the galaxy is. Now, the first step to doing that is understanding where my cursor is. You see this tiny bump here. You see a slight brightening, where Richard is pointing. And we are trying to understand whether that's produced by ionized oxygen in the galaxy. If it is, then we have studied that in laboratories. Astronomers have studied that in laboratories. We know what the wavelength should be. And then in the laboratory, we know what it should be. But because the universe has expanded between light leaving that galaxy and now that we're measuring it, from that we can estimate its redshift, the expansion amount of but the rate at which the galaxy is moving away from us, and then from that, its distance. So sort of indirect, but yes, that's how we measure distances to distant galaxies, like this one. I can tell you just If that is oxygen 2, one of the first things I can tell you is the universe is expanded by roughly a factor of 2 between light leaving that galaxy and now. That is, typical galaxies were twice as close when light left that space itself has stretched by a factor of 2 between light leaving that galaxy and now, if that line is an oxygen 2 line. That's a big if. We have to first establish whether that's an oxygen 2 line. Does that answer your question, David?
Yes.
Thank you. If there are questions from anyone else on the Zoom call, that would be great. And Raphael, Stefan, Richard, if you want to jump in with anything, please feel free.
Hi, my name is Samuel, and I am also from the 10th grade, and I have a question.
Please.
So earlier you've mentioned that the area where the telescope is supposed to be, I mean, like where it's kept, the room temperature, I mean, it's supposed to be in a cold area. And whereas we all know that in the galaxy also it's going to be really cold. So like what type of physics relates to the area where the telescope is and the atmosphere where, like the atmosphere surrounding the telescope outside the room and the galaxy?
That's a great question. And Samuel, that's a great question. Let me try and answer that. So the light from the galaxy has been traveling through space. Most of space is essentially a perfect vacuum. Essentially, most of space is empty. So light has been traveling through space for billions of years. And it's when it enters the Earth's atmosphere that it undergoes a little bit of distortion. This is what causes stars to twinkle. When we look at, you've all heard the nursery rhyme, Twinkle, Twinkle, Little Star. When light from a distant object like a star or a galaxy enters the Earth's atmosphere, while it's transparent, there are hot and cold pockets of air, and they have different refractive indices. Light travels at different speeds in hot versus cold air, and because of that, you get slight bending of that light, and you get this effect of twinkling. You've all seen bending of light. If you take, let's say, if you take a stick and you put it in, let's say you take a pencil and you put it in a glass of water that's half full, the pencil looks like it's bent because when light travels through water, it travels at a slower speed than when it travels through air. So this kind of bending of light is very common. And what we're trying to do, the reason we keep the telescope at the same temperature as the atmosphere is if we didn't do that, if we kept the telescope heated, we would get convection, which is hot air would be moving up from the telescope and would be right above the telescope when we're trying to observe distant stars. And hot and cold air have different refractive indices, and this turbulence in the air, and any turbulence in the air would cause stars to twinkle more than we'd like. The less twinkling there is, the sharper the images we can take with a ground-based telescope. Samuel, does that begin to answer your question a little bit?
Yes. Thank you.
Thank you. Let me bounce it back to Future Hope and see if there are any questions from the students there.
Hello, sir. I want to know what the telescope is measuring this radiation and all something special characteristic of the telescope or which kind of lens is being used.
I couldn't understand completely. Was the question which kind of lens is being used?
Some characteristic of the telescope. There must be some characteristic so that they measure this radiation.
Akia, could you please repeat the question since you're close to the microphone?
She's asking about which kind of telescope you all are using.
Oh, okay. So that's a very good question. Thank you.
And about the characteristics of the telescope.
Of course, I'll try to explain that. And what's the name of the student who asked, please?
Her name is Rupashi Das.
Rupashi. Okay, thank you, Rupashi. That's a great question. So the kind of telescope we are using is not the kind of camera that you have on your phone. When you pick up your phone and take a picture, your phone uses something called a lens to capture the image, right? You've all taken selfies or you've taken pictures of friends with your phone. That uses lenses to take images. We are using primarily a mirror, not a lens. So this is more similar to, let's say, a mirror in a bathroom where you might look at your own face in a mirror. So this is a mirror that's not flat, it's curved slightly. It's a concave mirror whose diameter is 3 meters. That's the primary, it's called the primary mirror. It's the main reflecting surface. So light bounces off that primary mirror. And because it's coming from a great distance, this light is coming from a distant galaxy or star, the light, when it's coming in, is parallel rays. And after bouncing off a concave mirror, it becomes a converging beam. This converging beam then goes through, bounces off a second mirror. That's a convex mirror, it's this mirror. And that, after the second bounce, it goes through a hole in the primary mirror and goes into what is called a spectrograph. This thing that is producing the spectrum is called a spectrograph. It's named after the people who donated money for the building of the spectrograph. It's called the Kast spectrograph, K-A-S-T is the name of the spectrograph. This is the thing that takes the light from the star and splits it up into the colors of the rainbow. Rupashi, does that answer your question? Yes?
Yes, sir. I understand his answer.
Thank you. Thank you. I realize I'm doing all the talking. So Raphael, Stefan, Richard, please feel free to chime in. Matt.
Hello, sir.
Yeah.
Hi, sir. My name is Franklin and I'm from Grade 11. I have a question. So you all said that oxygen and helium in the Earth's surface distort the wavelengths coming in. So is there a way of absorbing these wavelengths before they reach the Earth's surface?
So there are two separate things here. I didn't catch your name. Sorry. Please tell me your name again.
Franklina.
Franklina, I remember you. You gave us the tour of the school. How are you, Franklina?
I'm good, sir. How are you doing?
Good, thank you. So there are two different things going on here. The Earth's atmosphere both absorbs light and it emits light. So these elements like oxygen and ozone and OH and water, these molecules and atoms and ions, they produce these bright horizontal lines that you're seeing in the spectrum. Okay, and there is no easy way to remove them, but except in software, what we can do, and I'll describe that in a moment. So that's one of the things the Earth's atmosphere does. It glows at certain wavelengths. The other thing it does is it absorbs light at certain wavelengths. And the absorption of light is what you're seeing as the dark band that's going across a little bit below where Richard's cursor is. That dark band, that is produced by oxygen and OH in the Earth's atmosphere. So you can see it both absorbs light at certain wavelengths, and it also emits light at some other wavelengths. Now, the way we correct for both of these things, how do you correct for absorption? What we do is we point the telescope at a very hot star that has a very smooth spectrum. Okay, that we know intrinsically it should have a smooth spectrum. So when we see a dip in that spectrum, we know that dip is caused by the Earth's atmosphere. We can measure the amount of the dip and we can calibrate that out when we're taking a science observation. So that's something called flux calibration, that process. We use a second method, which is when that is to remove the glow from the bright glow. That method is called sky subtraction. What we do is, when we want to observe a star, we take a slit, we cut a slit in a piece of metal, meaning a rectangular opening in the piece of metal, and we let the light of the star shine through that rectangular opening. Now, why it's rectangular is because we want to look we want to take the spectrum on the star and off the star, because on the star, we're getting the light from the star and the light from the Earth's atmosphere. But off the star, we're getting light from the Earth's atmosphere alone. That's why if we go from left to right in this spectrum that Richard is displaying, from left to right, the left is one end of this rectangle, the right is the other end of the rectangle. In fact, the reason the Earth's glow looks like these horizontal lines, that's the shape of the rectangular cut in the piece of metal that we're using. So what we do is this spectrum that Richard is displaying, the thing labeled untitled.
Sir, we can't hear you.
Oops, you can't hear me now? Can you hear
Hello.
me okay now?
Now we can't hear you, sir.
Really?
I think that's on their side because Roger, we can hear you.
Yeah, the others can hear me.
Yeah.
So your audio is not coming to us.
Not even now?
Can you hear me? It might be on their side. Yeah.
Can you hear any of us? Could you hear us before?
Yes.
Now you can hear us?
Yeah.
Okay. I don't know why it stopped, but now if you can hear me now. Yeah, so the horizontal lines that are produced by the Earth's atmosphere, they look horizontal because we're using a rectangular cut in a piece of metal that's shaped like a long line, the rectangular cut. So of course the Earth's atmosphere glows everywhere, so it uniformly fills that rectangle. That's why we get these long horizontal lines like that are produced by the Earth's atmosphere. And the vertical line is produced by the galaxy. I'm getting into very technical details. So what you've asked, Franklin, is a very good question. I know you're destined to become an astronomer, and you will study this in great detail as you get deeper into this. Great question. And how is Anvesh? He was the other one who gave us the tour, right?
Come say, Ani, come on.
Hi, sir.
Hi.
Thank you, sir.
Thank you.
More questions?
Richard, can we show I'm going to stop my, I'm going to hand back control to you. Can we please show the blue half of the spectrum?
Yeah.
The other thing that the atmosphere does to light as it goes through it is scatters it a bit, but that kind of acts a little bit like absorption / emission. So kind of get lumped in, but does make things look fuzzier when they otherwise might not.
Yeah, so here you're seeing a spectrum of the shorter wavelength light. Beautiful, this is really beautiful. That bright emission line is that's green light that's produced by oxygen in the Earth's atmosphere. That's 5577. Some of you on this call may be familiar with something called the aurora borealis. Do you know what that is? Aurora borealis or aurora australis. They're called the northern lights or southern lights. Have the students heard about aurora borealis? Yeah. Have you ever seen any video of the aurora borealis, northern lights or southern lights? Have you seen it? Have you seen videos of it, or have you seen it directly with your own eyes?
In movies.
In movies, okay. What color would you describe for the northern lights? Green. Green. Yeah. Yeah, green and blue, but the green comes from this particular vertical line that Richard is pointing to. It's produced by oxygen in the Earth's atmosphere. It's particularly intense near the poles. This oxygen is excited by the magnetic field and solar particles. entering the Earth's magnetic field and atmosphere, but even in a relatively quiet part of the Earth's atmosphere, not near the poles, you can see this intense line, and the blue part of the spectrum, everything is rotated 90 degrees. So the Earth's atmosphere produces vertical lines now, and the distant galaxy produces the horizontal line that you see. One of the really cool things in this instrument we're using is something called a dichroic, DICHROIC. So you know that DI, whenever you see DI, di means two, right? We often, where do we come across di as two? Let me think of words. I'm thinking of the word dipole, but there are simpler words. BI also means two. Bicycle has two wheels, but di also means two. Chroic, CHR, is related to color, right? Chromatic. So dichroic is a special piece of glass that is put into the light path as soon as the light enters this instrument called the Kast spectrograph. And what that does is light that is the longer wavelength than green light, so yellow, orange, and red light, goes straight through this glass. And shorter wavelength light, what is shorter than green is, it's violet, indigo, blue. That gets reflected by the glass. So the yellow, orange, and red light go through the glass, and violet, indigo, blue gets reflected by the glass. So it splits up the light according to wavelength and sends the red light into one channel, sends the blue light into a different channel. Within each of these, there's something that's like a prism or a grating that splits up the light into the colors of the rainbow. So we essentially create two rainbows, one for violet, indigo, blue, green part of the spectrum, and then another for the green, yellow, orange, red part of the spectrum. So you can see that in astrophysics, like we're doing at the telescope today, there's a lot of physics, there's a lot of chemistry, there's some engineering, different kinds of engineering, optical engineering, mechanical engineering, electronics engineering. So many of you have interests in different areas, but you can see that it takes many kinds of subject expertise to build an observatory or use an observatory. Okay. Let's see.
Hey, Raja, I was going to go ahead and show a dichroic.
Oh, perfect.
Here.
Perfect. Thank
you.
You.
Yeah. Let me see if I can turn around my video here.
And you can share your screen if you want.
Well, I'm in the telescope right now, next to a box of dichroics.
Okay.
Let's see. So, let's see. Here's the telescope. Here's the box of dichroics. This is an old dichroic we don't really use anymore, 46. And I'll see if I can find this light.
And when you say 46, Matt, that means 460 nanometers is the split, right? Anything shorter than that gets reflected, anything longer than that gets transmitted.
Correct, yeah.
And we're using the D57.
Yeah, I gotta figure out how to change the. There we go. Okay.
And the dichroic that we're using is D57. Wow, look at that. Okay, so it's a piece of glass.
This is 46.
And if you hold it at a 45-degree angle, what happens? If you hold it at a 45-degree angle? Maybe along the other axis, tilt it along the other axis. I can't detect any change of color, but I'm colorblind.
Yeah, there's a little bit of a change of color.
Yeah. So this looks clear to me, and then as it gets more
yellow.
Yeah, it gets yellower.
Gotcha. And gets clearer, meaning probably it's letting in blue light.
Mm-hmm. Yeah.
And let's see, I've got These are the diacroics we use, change out on a daily basis. This is the 55.
Okay.
Pretty similar. Oh no, that one's completely different.
Right. Okay. You can really see it looks much redder. The
Yeah.
red
And
light's
now,
coming through. Yeah.
yeah,
And
when
then,
you shift
yeah,
it, it
turn
looks
it.
kind of like the
Oh
46
wow.
looked.
Wow. That's
It's nice
beautiful.
diacroic.
Can you guys all see it? The students, can you all see how it looks redder when you look through it? Because red light is coming through and blue light is being reflected. So it's actually doing a job of splitting the light.
And so yeah, if I look at it this way,
in
you can see the
reflected
red
light,
or
it
the
looks
blue
blue.
light reflecting. Yeah.
Yeah, in reflected light, it looks blue, and in transmitted light, it looks red. Beautiful. And I quickly got a glimpse of the telescope. It would be cool for students to see what that telescope looks like. This is a huge telescope. Yeah. Look at that. That yellow ring is 3 meters in diameter.
Or to hold the mirror.
That's where the primary mirror sits. You can't see the mirror. You're looking at the underside of the mirror, and it's protected by this metal ring. But the telescope is very long. The telescope is the size of 4 or 5 story building. Height of the tube is the size of a 4 or 5 story building. The lights are on. It's inside. It's a dome-shaped structure. The lights are on inside the dome. Yeah, there we go.
Yeah, since we're not open, I can actually go up to the mirror and show everybody. So I'm on a forklift right now.
Wow.
And
it's a forklift that you yourself are operating, right?
Yep. Let's see, so you see these are the mirror leaves. If I put my phone in here.
Oh yeah, you can see the mirror right there. You're seeing a reflection. That's why yeah. Do you see these what look like petals, metal petals? They protect the mirror. When they close, they protect the mirror.
Yep. And then yeah, here's another shot of the mirror. It's gonna tell that it's a mirror because
you can see a reflection from it.
Yeah.
This is on a mountaintop in California. The height of the mountaintop is, let me see if I remember, it's about 4,000 feet, 4,200 feet, if I remember correctly, which is something like
4,200.
4,200, right? That's feet. So you'd have to divide that by 3.3 to convert to meters. So it's a little under, it's about 1,350 meters above sea level is where the telescope is. And while I have you here, Manan, if you could please tell everyone where you are and your connection with our group, that would be inspiring for the students at Future Hope and Shanti Bhavan to hear. So Manan, please go ahead, unmute yourself and introduce yourself, please.
Okay, so I recently graduated 12th grade from Delhi Public School, Dwarka. I'm currently situated in New Delhi, India, and I'm working with Salvation Group. I'm not really working, I'm currently learning to reduce data that they observe.
Thank you, Manan. And Salvation stands for Spectroscopic Analysis of Luminous Variables and Transients in Our Neighbor. So it's looking at stars that pulse in our neighbor, meaning in the Andromeda galaxy. And Manan, where are you off to college in the fall? I haven't asked you.
I have decided to take gap year.
You're taking a gap year, okay. Do you know, and then you'll apply to college again, or have you deferred?
No, I'll apply colleges again, mostly in India this time.
Okay, gotcha. Okay. Oh, it's very good to see you. And Manan, if you don't mind my asking, you've turned 18 already?
Yes, I turned 18.
Okay. So you're just a few years older than the students in Shanti Bhavan and Future Hope. Yeah,
I mean, this year March I was going to school and now I'm not.
What is that again? Say that again.
I mean, I was going to school till March this year. So
oh, wow. So you're just out of school. You haven't been out of school for very long. There's a question. I see a hand up in Future Hope. Please ask your question.
Hello, sir. I am Kast from class 10.
And I have a request to you that we want to see a picture of our galaxy.
Of course. I can do that. I can share my screen. And Sumit, I remember you very well because we had a good laugh when we were when you were telling us.
1999.
1999, I remember. I still remember 1999. Okay, I'll show you can I show you a picture of the Andromeda galaxy, perhaps? Is it okay if I take over screen share and show a picture of Andromeda? Raphael, Matt, Richard, Stefan, is that okay if I do that?
Yeah, I don't have a problem with it. I think we're waiting for the dome to dry off if that even happens tonight. So
right, okay.
Yeah.
And say your name again, Sumit, is it? What was your name again? At Future Hope, what was your name? What's your name? You're muted. Right, let me see if I can show a picture of Andromeda. I'll try and do this. All right, I'm about to share my screen with you and show you some pictures of galaxies. Sumit, you asked the question, or is that your name, Sumit? 1999, what is your name?
Yes, sir. I can't hear you.
What's your name?
Yes, sir. I just have a request to you that we want to see some pictures of galaxy.
Right, and can you hear me okay?
Yes, now I can hear you, sir.
Okay, and your name is Sumit, is it?
Yes, sir.
Okay, Sumit, would you like to see a picture of our Milky Way galaxy or a picture of a different galaxy?
Actually, the connection is slow. The voice breaking. The voice is breaking.
It's breaking. Okay, let's try this. Let me share my screen, and let's see if this works.
Okay, sir.
Please let me know if you can see my screen now.
Yes, sir, it is visible.
Yes, sir, it's visible.
Okay. Do you see a picture of, do you see a dark screen with blue on it now?
Yes, we can see, sir.
Okay, so this is a picture of the Milky Way. And I'm going to remove it. And what you're going to see is a time lapse of the Milky Way. Tell me what you see, please. Okay, I'll play this movie. You saw a movie, right?
Yes, sir. The video is going on.
You're seeing a video. Okay. What is this a video of?
The sky with full of stars.
Yeah. So what is the Hindi name for this band of light?
What's Hindi?
What's the Bengali or Hindi name for it? Dhruva. No, this is called Akash Ganga. This is called Akash Ganga, which means river, river in the sky, right? Yeah, river in the sky. So this is our Milky Way galaxy. And can you tell why it looks like it's rotating like this?
Because we are rotating the camera.
Say that again.
Sorry, sir. Nothing, sir.
Why do you, okay, I'll play it one more time. Why do you think it's rotating like this? It's because we're observing it from the Earth.
Because of the timing, sir, you have recorded it, the video in too long, and you have made it faster.
Yeah, it's a time lapse. It's true, but the reason it's rotating is because the Earth is rotating. Okay.
Yes.
So I'll show you another video. This particular video that you just saw was put together by a physics teacher in California. His name is John Rockman. You see his name at the bottom. I'll show you another video. This time one was put together by a different person. His name is Aryeh Nirenberg. And in this case, what he did was, because the sky appears to rotate as the Earth rotates, he kept rotating the camera to keep track of the stars so that the stars would not rotate across his image. And when he did that, this is what he saw. Can you see the rotation of the Earth? Would you like me to play that again? Would students like to see that again? Yes or no? Would you like to see it again?
Yes, sir.
Yes, sir. We would like to see once again.
Okay, so I'm going to start it again. This time, pay attention. This glow at the bottom of the image, where the lower left of the image, what do you think this glow is coming from? This glow or this glow? Along the horizon. Probably from neighboring cities, from the setting sun. So that's where the glow is coming from. You'll see spots of light that are moving across. Those are aeroplanes that are going overhead. You'll see that. Okay, I'll start. You saw a plane go by right there. See another plane go by. I've deliberately stopped it because can you see these thin black lines going across where my cursor is? Can you see my cursor? Can you see this?
Yes, sir.
Can you see, do you know what those thin lines are?
Dark, it can be a wire or something.
What, sorry?
So dark lines. I think it's a wire or something.
It's a wire, exactly. It's probably telephone lines or power lines, something like that. That's what you were seeing. I'll start the video again. Could you all see planes going by? Very good. Could you see planes going by in that? Could you see airplanes going by, like streaks of light going across?
No, sir. We can't see the aeroplanes doing.
You could see it. Okay. Here's a picture of a different galaxy. This is the Andromeda galaxy now. Beautiful image. I didn't take this image. One of my colleagues took this image. This is Andromeda over here. These are two smaller galaxies. This galaxy in the lower right is called M32, Messier 32. The galaxy above Andromeda is called NGC 205, New Galaxy Catalog 205. 205 is the number, catalog number. And then Andromeda has another name. It's called M31. It's the 31st object in the Messier catalog. And then what you're seeing should be appearing gradually is a picture of two telescopes in Hawaii on Mauna Kea that we use to study the Andromeda galaxy. Here's Andromeda again with the full moon for reference. Andromeda is quite big in the sky compared to the full moon, except our eyes can't see it so well. So with the image, with the digital image, you can see much better. You can see Andromeda much better. I'm going to show you another movie. This time we're going to zoom into Andromeda. There's Andromeda over there. This is Andromeda is about 2.5 million light years away. So light takes 2.5 million years to travel from Andromeda to us. And this big arc is the Milky Way, is our own Akash Ganga, is our own galaxy. So we're going to zoom in and let's see if this works. Yeah, so you should see a movie soon. We're going to zoom in towards Andromeda. Can you see zooming? Is Andromeda getting bigger for you?
Yes, sir. Yes, sir. We can see the zooming.
Okay. What do you see now on your screen?
So we are going inside a galaxy. Yes, we are entering one galaxy.
How would you describe
this? Some stars here.
Okay, so why do you think there are all the stars the same color?
No, sir, I don't think all the stars are the same color.
So what colors do you see? What? How would you describe the colors?
Blue, red, blue.
Yeah. Okay, very good. Blue and red, and orange and yellow in between, I suppose, and white. Why do you think the stars have different colors? Why do different stars have different colors?
Because of the temperature.
Temperature, very good. The temperature. So red stars are low temperature. The sun in this picture would look sort of yellow. There's some yellow dots in this picture. The sun would look like. Do you know what the temperature of the sun is on the surface? It's about 6. It's about 6,000 Celsius. Or yeah. Or are you familiar with the Kelvin scale? Kelvin. Shanti Bhavan and Future Hope. Are you familiar with the Kelvin scale?
Yeah.
Okay, so the temperature of the sun's surface is about 5,900 Kelvin. Now, the blue stars, the stars that look blue in this picture, have a much higher surface temperature. Their temperature might be 40,000 or 30,000 Kelvin. And the stars that look red in this picture, their temperature is much lower. They could be as low as 2,000 or 3,000 Kelvin. So can you guess what telescope was used to make this picture? It's a very famous telescope. Which one? Hubble telescope. Yeah, it in fact said that, Hubble image. So Hubble telescope was used. Very good. Would you like to see this movie again?
Yes.
Okay, let's go back. Again, we're going to start zooming in now.
Best quality. Whoa. Whoa.
Okay, so let's see. Let me stop my screen share for a minute and ask the question. I want to keep track of time. It is well past when we were supposed to end the shadow session. But how are things going on at the observatory? Richard and Stefan and Raphael, Matt, is the dome still closed?
It is closed, and I think, yeah, we're almost at 12 degrees. So I was going to see, I can open it again to see if it's wet. Last time I did that about 40 minutes ago, it was still wet.
Okay.
So it's up to y'all if we open again to check it, or what you want to do.
Might be good to check just one last time before we call the night, and then that would be great, Matt. Thank you.
Great,
I know
yeah.
that this is the second of 2 nights we have. So to the group, to the student groups in particular, this project that we're working on, that Raphael, Richard, Stefan, and I, and Manan, and Monica, our collaborator. Monica's also from India originally. She's from Manipur originally. She's based in Hawaii now. Monica and I have been working together for the last 5 years. We started working together in 2018. We are working on a project called Salvation, which stands for, it's an acronym, spectroscopic, S for spectroscopic, A for analysis, L for luminous, V for variables, which is a kind of stars whose brightness varies with time. Spectroscopic analysis of luminous variables and transients. Transients are sources of light that come and go, that disappear and appear and disappear. So spectroscopic analysis of luminous variables and transients in our neighbor. In our neighbor refers to our neighboring galaxy, Andromeda. It's the nearest galaxy that's bigger than our own. And so the Salvation project has been going on for a few years. And this semester, the second half of 2023, second half of this year, we've been awarded 10 nights, 2 nights in August, 2 nights in September, 2 nights in October, November, and December. So this is our second of our September nights that's just finishing up here in California. I know it's Monday afternoon in India, but it's early hours of Monday in California, very early hours. It's like 5 a.m. So the sunrise is about half an hour away. I know we've stayed well beyond the time we promised you. And please tell me, Shanti Bhavan first, and then Future Hope. Do you need to go to class, or do you need to do something else now? Please let me know. I don't want to keep you any longer than we promised this session would last. Shanti Bhavan, how are your time constraints? Do you need to go?
Yeah, we should get going around 5:30. So
okay, it's 5:30 for you. Has this been fun?
Yeah.
Sorry, Brianna, go ahead.
Yes, thank you so much.
Would you like to do this again?
Oh yes, thank you so much.
So we'll have many of these
Yeah, it's
coming
really
up.
informative.
So we'll have many of these sessions coming up in October on a different telescope, on a telescope in Hawaii. I'll be in Hawaii for that. I'll let you know. Do you think other students from the school might be interested?
Yeah, definitely.
Yeah,
that'd be very interesting.
Please tell them what it was like. Tell them, which parts of it were fun, which parts of it were boring. Please tell them so that they can come in with their eyes open. Same thing for Future Hope. It's what, 5:30 in the afternoon now for you? 5:28.
Yes, it's 5:30 now.
Okay. Do you need to go, or and would you like to do this again?
And after this, we need to go home.
Okay. Go home. Okay.
School hour is finished at 2:10.
Yeah,
Okay.
our school hour is over at 2:30.
Okay. So you stayed well beyond school hours. Are all of you going home now?
Yes.
Okay.
Yes, we will go home.
So we'll be in touch with your teachers. Kea, with you, I don't have your email, Kea, but I'll contact Minu and Shamarjit and Shujata to let you know when our next options are for signing up like this. If there's other times of the day, we'd love to make this happen. Same thing for Future Hope. If there are other students from other classes who might be interested, please let me know. Now, today you saw a session on astronomy. In the future, we might be able to showcase sessions on biology, other kinds of research. So I'll let you know as those become available. Thank you. Thank you, everyone. Thank you to Future Hope. Thank you, Shanti Bhavan.
Thank you so much.
Thank you, sir.
Thanks, Ted. Bye. I'm going to stop the recording.